Hello everyone. Let's have a class. Okay, in the next 1 hour, we are going to talk about the decoder. In the course 2 weeks ago, we have already talked about the encoder. In the next 1 hour, we are going to talk about the decoder. There are two kinds of decoders. I'll spend more time introducing the common one later. The common one is called Autoregressive Decoder. How does this autoregressive decoder work? We will use speech recognition or machine translation used in homework as examples to explain it to you. The mechanism of these two tasks are the same. The difference between these two tasks is their inputs and outputs. How does speech recognition work? Speech recognition, as you know, is to input a voice and output a string of text. You will input a piece of voice to the encoder. For example, you say machine learning in Chinese to the machine. The machine receives an audio signal and put it into the encoder. What will the output be? The output will become a row of vector. We spent a lot of time talking about the encoder last week. What kind of content is in the encoder? It's very complicated. Forget it if you do not remember. You should only remember that what the encoder does is to input a vector sequence and output another vector sequence. Next, it's the decoder's turn to operate. What decoder has to do is generating an output sequence. The decoder generates the result of speech recognition. How does the decoder produce the speech recognition result? What the decoder does is to read the output of the encoder first. As for how the decoder reads them, we will talk about it later in class. You can first assume that somehow there is some way to put the outputs from the encoder into the decoder. We will deal with this step later. How does the decoder generate a word sequence? The output of the speech recognition machine is a word sequence. How does the decoder generate a word sequence? First of all, you have to give it a special symbol. This special symbol represents the beginning. In the teaching assistant slide, it is written as begin of sentence. The abbreviation is BOS. I am afraid that you do not know what BOS is. So I write it out clearly. It means the beginning. It means begin. Then this is a special token. You can add this special token to your lexicon. Lexicon defines what words the decoder might generate. Add this special symbol. Add this special word. This symbol or this word represents the beginning. Represent the beginning of the sentence. Okay, so the decoder has this special symbol. In the machine learning community, suppose you want to deal with NLP problems. Each token can be represented by a one-hot vector. The one-hot vector consists of zeros in all dimensions, except for a single one in one of the dimensions. Begin is also represented by a one-hot vector. One of the dimension is filled with 1, and other dimensions are filled with 0. Okay, next, the decoder will generate a vector. What's in this vector? What's in this vector? The length of this vector is very long. Its length is the same as the size of your vocabulary. What does the vocabulary mean? You have to decide what the output unit of your decoder is first. Suppose what we are doing today is Chinese speech recognition. The output of our decoder is Chinese. The size of your vocabulary may be the number of Chinese square characters. How many Chinese square characters are there? Different dictionaries may give you different numbers. There are about 2,000 or 3,000 Chinese square characters in common use. The ordinary people may recognize about 4,000 to 5,000 characters. Then the rest are rare characters. You might not know how to pronounce it when you see it. You can't even write it out. So just consider, what Chinese square characters do you want your decoder to output? You just list them here. For example, if you want to make your decoder output the common 3,000 Chinese characters, list them in the lexicon. Decoders of different languages don't necessarily output different units. It depends on your understanding of that language. For example, in English, you can choose to output letters from A to Z. Output the English letters. You might think that the letter unit is too small. Someone may choose to output English words. English words are separated by blanks. But if you use words as the output, there are too many, so you will find that in the slide from the teaching assistant. The teaching assistant said that he used subword as English units. There are some ways to separate the prefix and root of the word. Take the prefix and root as the unit. I think it's relatively simple. If it's in the Chinese scenario, usually, you may use the Chinese square character as the unit. Then in this vector, the length of this vector is the same as the numbers of the square characters in Chinese. The same as the numbers of square characters you want the machine to output. Then every Chinese character will correspond to a value. A softmax function is usually passed through before generating this vector, just like doing classification. Before we get the final output for classification, we will pass the output through a softmax function. After passing through a softmax function, the score in this vector will be a distribution. That is, the values in this vector will add up to 1 for sure. After getting this vector, it is not the final output result. This vector will give each Chinese character a score. The Chinese character with the highest score is the final output. In this example, Chinese character G has the highest score, so G is regarded as the first output of this decoder. Next, you treat G as the new input of the decoder. Originally, the input of the decoder only has the special symbol, begin. Now besides begin, there is also G as its input. For G, it is expressed as a one-hot vector and represented as the decoder's input. So the decoder now has two inputs. One is the begin symbol. The other one is G. Based on these two inputs, it will get an output. It outputs a blue vector. According to this blue vector score, for each Chinese word, we will decide what the second output is. Which word gets the highest score is the output. Assume that Qi has the highest score. Then Qi is the output. The decoder will use Qi as the input. Now the decoder sees begin, G and Qi. Next, it has to decide what to output next. It may then output Shay. This process continues repeatedly. After the machine inputs Shay, Shay is used as the input again. So now the decode sees begin, G, Qi, and Shay. The encoder here also has input. We'll later discuss that for the encoder's input, and how the decoder handles it. So the decoder sees the input from the encoder. It sees G, Qi, and Shay. Next, it decides to output Shi. It will output a vector. In this vector, the Chinese word Shi has the highest score. So it outputs Shi. Then this process continues repeatedly. There is a key point here. We especially mark it with a red dotted line. In other words, the input seen by the decoder is its own output. At the previous time, the decoder will use its own output as the next input. The decoder will use its own output as the next input. So when our decoder is generating a sentence, it may actually see the wrong thing, because what it sees is its own output. If today, the decoder has a speech recognition error, for example, it misidentifies Qi as Qi, then the decoder will see the wrong recognition result. It still has to find a way to produce what it wants to produce based on the wrong identification result, and expects that it is the correct output. Then you might think that we let the decoder see the wrong input. We let the decoder see the wrong input produced by itself, and then feed it into itself. Will it cause a problem? Will it cause the error propagation problem? The so-called error propagation problem is that one wrong step can cause every following step wrong. Here, if you accidentally write Qi as Qi, will the whole sentence be wrong? Is it possible that there is no way to generate the correct vocabulary anymore? Yes, it's possible. Later, we will talk about how to deal with this problem at the end. Now, we ignore this problem and continue. Okay, then we take a look at this decoder. What does its internal structure look like? Here we temporarily omit the encoder part. In the transformer, the structure of the decoder looks like this. It's a bit complicated. It's slightly more complicated than the encoder. Let's put the encoder and the decoder together now, and compare the differences between them. Then you will find that if we hide the middle part of the decoder, then the encoder and the decoder won't have a big difference. Look at the encoder here. Multi-head attention. Then add and norm. Feed forward. Add and norm. We repeat it n times. The decoder is actually the same. When we hide the middle part, we will later talk about what's done in this hidden part. But when we hide the middle part, the decoder is also the same as the encoder. There is a multi-head attention. Add and norm. Then feed forward. Then add and norm. So for the encoder and the decoder, actually, there is no very big difference. Except for the difference in the middle. Except for the hidden part. The encoder and the decoder are the same. In the end, we may have another softmax function, so that its output becomes a probability. There is a slight difference here. On the decoder side, a mask is added to multi-head attention. In this block. What does this masked mean? The meaning of the masked is that this is our original self-attention. Input is a row of vectors. Output is another row of vectors. For each output of this row of vectors, it makes the decision after reading the complete input. So when outputting B1, it is actually based on all the information from A1 to A4 to output B1. When we transform self-attention into masked attention, what's the difference? The difference is that now we can no longer look at the right part. That is, when B1 is generated, we can only consider the information of A1. You can no longer consider A2, A3, A4. When B2 is generated, you can only consider the information of A1 and A2. You can no longer consider the information of A3 and A4. When B3 is generated, you can't consider the information of A4. When B4 is generated, you can use the entire input sequence information. This is masked self-attention. To be more specific, what you do is like this. When we want to generate B2, we only take the query in the second position, and the key in the first position, and the key in the second position, to calculate attention. For the third position and the fourth position, we just ignore it, and don't calculate attention. We ignore the right-hand side of A2 and only consider A1, A2, Q1, Q2, K1, and K2. Q2 only calculates attention with K1 and K2. And we only calculate the weighted sum of V1 and V2 at the end. Then when we output this B2, it only considers A1 and A2, but not A3 and A4. So why is it like this? Why do we need it to be masked? This is actually very intuitive. Well, think about how our decoder works at the beginning. It outputs one element at a time. Its output is produced one by one. So A1 is produced first, then A2, then A3, and then A4. This is different from the original self-attention. In the original self-attention, A1 and A4 are input into your model all at once. When we talked about encoder, it input A1 and A4 all at once. But for a decoder, there has to be A1 first before A2, then A3, then A4. So actually, when you have A2 and want to calculate B2, you don't have A3 and A4. So you have no way to take A3 and A4 into account at all. That's why, on the image of the decoder, Transformer's original paper emphasizes that it's not the usual attention. This is a masked self-attention. It just wants you to know that decoder's tokens are produced one by one. So it can only consider the things on its left. It has no way to consider the things on its right. Okay, to this point, we talked about how the decoder works. But here, there is a very critical problem. The problem is that decoder must decide by itself the length of the output sequence. But what should the length of the output sequence be? We do not know. You can't easily infer the length of the output sequence from the length of the input sequence. Just because the 4 vectors of input doesn't mean the output must be 4 vectors. In this example, the length of input and output are the same. But you should know that in real-life applications, this is not the case. The relationship between input and output length is very complicated. We expect the machine to learn by itself. When I give it an input sequence, it should know how long the output sequence should be. But using our current decoder's operating mechanism, the machine doesn't know when it should stop. After it outputs xi, it can continue to repeat the exact same process. Take xi as input. Then maybe the decoder will output guan. And it can just keep going until eternity. What does this remind me of? It reminds me of tweet solitaire. I don't know if you know what this is. This is like a tradition. On a forum called PTT. How does it work? A person will tweet a Chinese character first. For example, Chow. Next, another netizen will push another character that can follow it. So you can generate a row of characters. Line them up and you get this gibberish. Don't know what it's talking about. This process can last for several months without stopping. I don't know why either. So how do you stop this process? How can I stop it? Someone has to take the risk to tweet a Duan tweet break, and it will stop. So what we want the decoder to do is also the same. We want to make it output a break. So you have to prepare a special symbol. This symbol will act as the break. Here, we use end to represent this special symbol. So except for all the Chinese characters and begin, you also have to prepare a special symbol. End. Actually, in TA's program, the symbols for begin and end, signifying the start and the break, are the same symbols. It's okay because begin will only appear in the input, and end will only appear in the output. So if you study carefully, you will find that end and begin are actually the same symbols in TA's program. But if you want to use a different symbol, it's totally fine. No problem at all. Okay, so now, the decoder can output this end symbol to signify a break. Now, we expect that after she is produced and becomes the input of decoder, the decoder must be able to output end. In other words, after taking she as input, after the decoder sees the embedding output by encoder, begin, ji, chi, she, and she. After seeing this information, it needs to know that the process of voice recognition is over. There's no need to generate more characters. In its generated vector, the probability of end, the break symbol, must be the greatest in order for end to be output. Then, the whole process of decoder generating sequences will be over. Okay, so this is the way autoregressive decoder works. Next, we use 2 slides to briefly talk about non-autoregressive model. Non-autoregressive model is usually abbreviated to NAT. So sometimes the autoregressive model is abbreviated to AT. How does the non-autoregressive model work? For the autoregressive model, given begin, it will output W1. Then we use W1 as input, and the model will output W2. This process repeats until the model output end. For NAT, it isn't like this. Suppose we want to generate some sentences in Chinese. It does not generate one word each time. Instead, it generates the entire sentence at once. How can we generate the entire sentence at once? The input of the NAT decoder may be a whole row of begin tokens. You just use a bunch of begin tokens as the model input and make it generate a row of tokens at a time. For example, if you use 4 begin tokens as the input, the model will generates 4 Chinese characters, and it's done. It only takes one step to generate a whole sentence. Here you may ask a question. Didn't I just say that the model doesn't know? How many tokens should it output? How do we know? How many begin should we put in? Yes, there is no way to know this. There is no way to know directly. So, there are a few common solutions. For example, you can train another classifier whose input is the same as the encoder. What about the output? Output is a number. This number represents the length that the decoder should output. So you just train another classifier. This classifier use encoder's input as its input. Then, it will output a number. For example, it output 4. After that, NAT decoder will receive 4 begin tokens as its input. Then it generates 4 Chinese characters. This is a possible solution. Another possible solution is, you don't have to care about the input length. Just give it a bunch of begin tokens. Suppose that the output length is always shorter than 300. You just set an upper bound. Then, you just use 300 begin as the input, and it will output 300 words. Then, you should check the location of end in the output sequence. Afterwards, we ignore those tokens on the right-hand side of end. Then we done. This is another possible solution for NAT decoder. What are the benefits of NAT decoder? The first benefit is parallelization. For AT decoder, it output tokens one by one. Suppose you want to generate a sentence with 100 words. You need to do decode 100 times. But this is not the case for the NAT decoder. Regardless of the length, it generate a whole sentence in one step. So, NAT decoder is much faster than AT decoder. The idea of this NAT decoder is proposed after the invention of transformers and the self-attention mechanism. Because in the past, when we used LSTM or RNN, even if we give the model a row of begin, it still has no way to generate the whole sequence at once. It can only generate tokens one by one. So before the invention of self-attention, nobody wants to use NAT decoder. But since we have self-attention, NAT decoder has become a popular research topic. Another advantage of the NAT decoder is that you can control the length of its output well. How to say? Take speech synthesis as an example. Actually, NAT decoder is a very common model in speech synthesis. Nowadays, speech synthesis can be realized by a sequence-to-sequence model. The most famous model may be Tacotron. It's an AT decoder. While there is another model called fast speech, which uses the NAT decoder. The advantage of NAT decoder is that you can control the output length. As we have discussed just now, how to decide the output length of NAT decoder? You may have a classifier to determine the output length of the NAT decoder. If you are doing speech synthesis, suppose you want to make your system speak faster. Then, you can divide the output of the classifier by 2. It speaks 2 times faster. On the contrary, if you want the model to speak slower, you can double the output length. Your decoder will speak 2 times slower. So, if you have this kind of NAT decoder, and you have explicitly control the output length simultaneously, you have a better chance to control the output length of your decoder. You can apply them in many fields. Why does NAT decoder becomes a popular research topic recently? Although NAT decoder seems to have all kinds of power ostensibly, especially for the parallelization, the biggest disadvantage is its performance. It is usually worse than AT decoder. So there are many papers trying to boost the performance of NAT decoder. They try to make it as good as AT decoder. But if you want to make the NAT decoder be as good as AT decoder, you have to use a lot of tricks. For a normal AT decoder, NAT decoder requires a lot of effort to be comparable to it. Why is the performance of NAT decoder bad? There is an issue which we won't talk about in detail today. It's called multimodality. If you want to know more about NAT, the supplementary content provided by teaching assistants is here. NAT is also a profound subject. The teaching assistant gave you a rough description of NAT for an hour and a half. So this is also a big topic. We can't talk in detail about it today. Just tell you, there is NAT task in the world. Then we will talk about how do encoder and decoder interact with each other. This means we are going to talk about the part we deliberately masked. If you observe this part carefully, this part is called cross-attention. It is the bridge between encoder and decoder. In this part, you will find that there are 2 inputs from the encoder. The encoder provides 2 arrows, and the decoder provides an arrow. The decoder can read the output of the encoder from the 2 arrows on the left. How does this module actually work? We will actually show you the process of its operation. Okay, this is your encoder. Input a row of vectors, and output a row of vectors. We call it A1, A2, A3. Next, it's your decoder. The decoder will take a special token begin at first. After reading the special token begin, you may go through self-attention. This is a masked self-attention. Then get a vector. Even though it's a masked self-attention, the length of output vectors is still the same as the input vectors. So input a vector and output a vector. Then make a transform for output vector by multiplying a matrix. Get a query called Q. The A1, A2, and A3 here also generate key K1, K2, K3. Then multiply Q with K1, K2, and K3 respectively to calculate the attention score. Then obtain alpha 1, alpha 2, alpha 3. Of course, you may also do softmax for a little bit of normalization. So I add prime. It means it may have done normalization. Next, multiply alpha 1, alpha 2, and alpha 3 with V1, V2, and V3. The weighted sum of them denote as V. The vector V will pass through the fully connected layer to do the next processing. In this step, Q comes from the decode. K and V come from the encoder. This step is called cross-attention. So the decoder extracts the information by generating Q to interact with the encoder. The information is the input for the fully connected network of the decoder. This is how cross-attention works. Now, we generated the first Chinese character. When we want to generate the next Chinese character, the operation is the same. Enter begin and first Chinese character. Generate a vector. The vector is transformed by multiplying a matrix and obtain Q prime. Get a query Q prime. Again, we use Q prime to multiply with K1, K2, and K3 to calculate the attention score. Again, we multiply attention score with V1, V2, and V3. Then add them up to get V prime. Pass through it to the next fully connected network. This is the operation process of cross-attention. There is actual cross-attention in the literature, showing its effectiveness. But I want to explain a little bit. This picture is not from Transformer. The title of this paper is called Listen, Attend and Spell. This is the earlier successful article that using sequence-to-sequence model on speech recognition. It was published in ICASSP 2016. I remember ICASSP 2016 was held in Shanghai. I also heard this paper report. There were huge crowds of people then. Everyone thinks it was amazing that sequence-to-sequence model can do voice recognition, and the result only has a little bit gap compared with state-of-the-art method at that time. The results in this paper show that sequence-to-sequence models still lose the state-of-the-art method, which was the best speech recognition system at the time. But there is just a little gap. So let everyone think that it seems potential for sequence-to-sequence model to be used in speech recognition. So it's not actually the transformer. At that time, the encoder and decoder were both LSTM. But the cross-attention mechanism was already used at that time. So, there was already a mechanism like cross-attention before transformer. There was just no self-attention mechanism. So cross-attention was published first, and self-attention was published later. At that time, if you use sequence-to-sequence model, I don't know why. The paper's title must contain 3 verbs. There must contain 3 verbs at that time to represent that you use a sequence-to-sequence model. So, like this one, listen, attend and spell, shows that the machine should listen to the sound, and then do attention, across attention. Finally, spell out what it listens. Then I show this picture to you. Make it easier to imagine how the cross-attention work. Okay, this segment is a sound signal. It is the input of the machine. When the sound signal is input to this encoder, it is represented by a string of vectors. A string of vectors. This is time. Then there are vectors row by row. Then this row is the output of the decoder. The decoder only spit one English letter at a time. So it will spit H, O, and W sequentially to spell how. If it has reached the boundary of a vocabulary, it will automatically spit out blanks. Blank is a special token. So the machine may output blank. Means that the vocabulary is over and needs to spell new vocabulary. The next output are M, U, C, H. And then a blank again. Then output W. This sentence is a tongue twister in English. The complete sentence of this sentence is, how much wood could a woodchuck chuck? It doesn't matter what the content is. It's only a tongue twister. That's amazing. The machine can output one character at a time, and can generate the correct vocabulary. Okay, what does the value here mean? The value is the score of attention. So when you want to generate this H, before generating this H, the decoder will do attention to the output of the encoder. So it attends in this place and produces H. Then attend this place to produces O. Attend this place to produces W. The darker the color here means that the attention score, alpha greater. So you will find that when it produces to H, it hears the sound of H in this place, so it produces H. Then move a little bit to the right to produce O. Move a little bit to the right to produce W. After that, attend here to generate space. Then attend here to generate M. You will see the weight of the attention moves from the top left to the bottom right. It's very similar to the mechanism that you think attention should operate. Because every time we generate a vocabulary here, the audio signal we want to focus on should be from the left to the right. So if you look at model attention, it may also be from the top left. Its highest score may also be from the top left to the bottom right. Speaking of that, maybe some students will ask, the encoder has many layers, and decoder also has many layers. From the previous explanation, it sounds like, no matter which layer of this decoder is, it takes the output of the last layer of the encoder. Yes, the implementation in the original paper is like this. Does that have to be like this? No, it doesn't have to be this way. You can always bring some new ideas on your own. So here I am quoting a paper to tell you. Some people try different ways of cross-attention. The encoder has many layers here. And decoder has many layers, too. Why does every layer of the decoder have to take the output of the last layer of the encoder? Can there be a variety of different connection methods? This can be a research question to study at all. Okay, in the end, we are going to talk about training. We have already talked about encoder, decoder, and how encoder and decoder interact. We have already. You have clearly stated that how to get the final output from an input sequence. Then we will move forward to the training part. We haven't talked about the training part yet. What we've talked about is, supposing that after your model is well trained, how does it do testing? And how does it do inference? The inference is indeed testing. So when I say inference, I mean testing. They are the same. So how to do training? Next, I will talk about how to do. If it is for speech recognition, then you need to have training data. What kind of training data do you need? You have to collect a lot of audio signals. Every audio signal must be heard by the servitor to type out what the corresponding vocabulary is. Servitor listens to this passage, which is machine learning. Then he types out the words, machine learning. So you know that your transformer should learn to output machine learning when hearing this sound signal. How can machines learn to do this? We already know that when the input is this audio signal, the first output word should be G. So, when we put begin token to this decoder, its first output word should be as closer to G as possible. What is the closer the better means? The word G will be represented as a one-hot vector. In this vector, only the dimension corresponding to the G is 1. All the others are 0. This is the ground truth. Then the output of our decoder is a distribution, a probability distribution. We hope that this distribution is closer to this one-hot vector. So you will calculate the cross-entropy between ground truth and this distribution. Then we hope that the smaller value of this cross-entropy is, the better it is. That's all. You may find that this task is very similar to classification. Yes, it is very similar to classification. The TA mentioned this when he explained the homework just now. You can think of it as every time decoder generates a Chinese character, it does a classification task. There are 4,000 Chinese characters. Therefore, that is to do the classification task with 4,000 categories. Okay, so actually it looks like this during training. We already know that the output should be the 4 words of machine learning. Then you tell the machine. Tell the decoder. The first output, the second output, the third output, and the fourth output should be the one-hot vectors of these 4 Chinese characters. We want the outputs to be Closer to the one hot vector of these 4 words the better. During training, every output will have a cross entropy. Every output and one hot vector. The ground truth corresponding to it has a cross entropy. Have a cross entropy. We want the sum of all cross entropy to be lower. The lower the better. So here are 4 classification tasks. We hope that the cross entropy sum of these classification tasks is as low as possible. But don't forget there is an end token. So, suppose this sentence has 4 Chinese characters. But when you are training, what you want the decoder to output is not only these 4 Chinese characters. You have to ask it to remember that after these 4 Chinese characters, output this special token end. So you have to tell your decoder that the cross entropy of the last output vector at the 5th position and the one hot vector of end token should be as low as possible. Then this is the decoder training. You give ground truth, the correct answer, to it. Hope that the output of the decoder is as close to the ground truth as possible. There is something worthy of our attention. The thing is like this. Look at the input of decoder. Which is the ground truth? We will show the decoder the ground truth during training. That is, we will tell it that given begin and G, it should output Qi. Given begin, G, and Qi, it should output Shay. Given begin, G, Qi, and Shay, it should output Shi. Given begin, G, Qi, Shay, and Shi, it should output end. During decoder training, we will give it the ground truth. This is called teacher forcing. I am not sure why it's called teacher forcing. It seems like the teacher will force you to do something. Doesn't sound great. But this skill is called teacher forcing. That is, we put the ground truth as the input of the decoder. Then you will have a problem right now. During this training, the decoder has peaked at the ground truth. However, when testing, obviously there is no ground truth to show to the decoder. I also emphasized that when we using this model for inference, what the decoder sees as its input, there is a mismatch. There is a mismatch. Later, we will have a slide of explanations about the possible solutions. What's next is to talk about training transformer. There are some tips for training transformer or sequence-to-sequence model. It's not limited to transformer. The first tip is the copy mechanism. For many tasks, in our discussion, we make the decoder generate its own output. But for many tasks, maybe the decoder does not need to create the output by itself. What it needs to do is to copy something from the input. Is there any way we can make the decoder copy something from the input? In fact, there is a way. Which tasks can use the copy mechanism? The chatbot is an example. For example, people say, "Hello, I'm Kololo," to the machine. Kololo is the leader of Phantom Troop. It doesn't matter who he is. I haven't seen him for a long time. I am Kololo. What should the machine reply? The machine should answer, "Hi Kololo, nice to meet you." For the machine, it is not necessary to create the term Kololo. This must be a very weird word for machines. So it may be difficult. It may not appear in the training data even once. So it is unlikely to correctly generate this vocabulary or this sentence. But suppose when the machine is learning, what it learned is not the 3 Chinese characters of Kololo. It learns when it sees the input of I am someone. It just copy someone. No matter what it is. Training of such a machine will be easier. It is more likely to get the correct result. So, copying for dialogue is a required skill and ability. Let me give another example. Gon can't use his nen. He can't use his nen. You might answer, what do you mean by not being able to use nen? For the machine, repeating this paragraph that it doesn't understand doesn't need to create this paragraph from scratch. It may learn from users. From human input to copy some vocabulary as its output. When doing a summary, you may need skills like copying. The so-called summary is that you have to train a model, and this model will read an article, and then generate a summary of this article. There is a way to do this task. You just collect a lot of articles. And every article has a summary written by someone. You train a sequence-to-sequence model. It's done. To do such a task, you can't do it with a little data. Some students collected tens of thousands of articles. Then train a sequence-to-sequence model, and found that the result is a bit poor. The students come and ask me why. I'll tell you that training a model to speak reasonable sentences usually needs millions of articles. So, if you have a million articles, and those articles have human-labeled abstracts, or you put the title of the article as an abstract, which spend less manpower to label, then you can train a model to help you read an article and make a summary. We know that when doing a summary, sometimes a lot of vocabulary is directly copied from the original article, right? When I was young, the teacher asked us to write a summary of the text in the Chinese class. You didn't create your vocabulary. You just find some sentences from this text and rewrite them. In fact, it becomes a summary. So, for the task of summary, copying some information from the article may be a very critical ability. Does the sequence-to-sequence model has the ability to do this? In short, yes. We won't go into details. The earliest model with the ability to copy things from the input is called pointer network. I've talked about it in class in the past. I put the video here for your reference. There is a deformation later called copy network. You can take a look at this paper. Copy mechanism in sequence-to-sequence. Any questions? See how the sequence-to-sequence model copies things from input to output. Okay, the sequence-to-sequence model is sometimes known as a black box. Sometimes you don't know what it learns. Sometimes it will make very low-level mistakes. What kind of low-level mistake it is? Here is an example of a real low-level error. The example given here is speech synthesis. For speech synthesis, you can just train a sequence-to-sequence model. Everyone is familiar with the sequence-to-sequence model. Transformer is an example. You take it out. For the input, you collect a lot of voices and correspondence between text and audio signals. Collect a lot of text and audio signal correspondence. Then, tell your sequence-to-sequence model that when this Chinese sentences are input, you need to output this sound. And then, end of the story. Just train. Then the machine can learn to do speech synthesis. So what is the result of the method like this? Well, not bad. For example, I asked the machine to talk fa chai 4 times. Let's see how it speaks. The output of the machine is like this. Fa chai fa chai fa chai fa chai. I found it amazing that I entered the same vocabulary, fa chai, for 4 times. The machine actually output with prosody. You may ask why it has prosody. Listen carefully. Fa chai fa chai fa chai fa chai. The tones of 4, fa chai fa chai fa chai fa chai, are not the same. Fa chai fa chai fa chai fa chai. It has cadence and frustration. How did it learn? I don't know. It's trained by itself and look like this. Then, you let it say, fa chai, 3 times. Fa chai, fa chai, fa chai. It's also fine. Then, you let it say, fa chai, twice. Fa chai, fa chai. It's also fine. Then, you let it say, fa chai, once. Chai, 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 chai. Why didn't it pronounce fa? Why didn't it do? We still don't know the reason why it's like this. It's that your sequence-to-sequence model sometimes will be trained to give inexplicable results. Maybe, in the training dataset, there is only few short sentences like this. So, the machine could not deal with it. We don't know how to deal with a very short sentence like this. You ask it to pronounce fa chai. It omits fa and only says chai. You dare to let it say fa chai 4 times. It's fine to repeat fa chai 4 times. But when it comes to once, there is a problem. It's so weird. Of course, this example does not appear so often. This sequence-to-sequence, which the TTS learned from, is not as terrible as you think. To find such a terrible example like this takes time. It takes much time to find such a terrible example like this. But it does exist. Okay, so what should we do? One possible solution is below. Since we just found out that the machine missed words, there are some things in the input that is ignored. Can we force it to read through everything from the input? It's possible. This trick is called guided attention. It's useful for this kind of guided tasks. I think it is most suitable for tasks like speech recognition and speech synthesis. Because for tasks like speech recognition, it's hard for you to accept the scenario below. You say a word. It is recognized, but with a section lost by the machine. Or, you enter a paragraph of text for speech synthesis. It is synthesized but with a section lost by the machine. It's hard to accept. If it's for other applications, for example, Chatbot, or summary, it may not be so strict. Because, for a chatbot, you input the sentence, and it just replies a sentence. Would it finish reading the whole sentence? You don't really care, somehow. You actually don't know. But for speech recognition and speech synthesis, guiding attention may be a relatively much important technology. What guiding attention is going to do is asking the machine to guide or to lead this attention process. When asking the machine to do attention, there is a certain way. For example, for speech synthesis or speech recognition, the attention we imagine should be from left to right. Fortunately, in this cases, we use the red curve to indicate the attention score. The higher the score, the greater the value of attention. Now, no matter it is doing speech recognition or speech synthesis, we take speech synthesis as an example. Then, your input is a string of text. Then, when you synthesize the voice, obviously it is read from left to right. So, the machine should first look at the leftmost input vocabulary to produce voice. And then it should look at the words in the middle to produce voice. And then it should look at the words in the right to produce voice. If you do speech synthesis today, and you find the attention of the machine is irregular, looking at the end first, then the front, looking at the whole sentence indiscriminately, it is obviously that something goes wrong. Obviously, something is wrong, or something goes wrong. Obviously, this kind of attention is problematic. When you do speech synthesis, you obviously can't get a good result. So, what guiding attention has to do is to force attention to have a fixed appearance. Then, for this problem, if you already understand that, for problems like speech synthesis TTS, your attention score and the position of attention should be from left to right. Why don't you put this limitation into your training to force the machine learning attention from left to right? How should we do like this? I put some key words here to let everyone Google it. For example, monotonic attention or location-aware attention. This part is also a big pit. I won't go into details and leave it to everyone to study. Well, there is another thing called beam search. The term of beam search, when the TAs are explaining the homework just now, is also mentioned. What is beam search? Let's take an example here. In this example, we assume that our current decoder can only generate 2 words. Let's assume that in this world, there are only 2 possible outputs. One is called A, and the other is called B. If there are only 2 words in the world, A and B. Okay, for a decoder, what it should do is, every time at the first time step, to pick one from A and B. After A is selected, it uses A as another input, and picks one from A and B. For example, it may choose B as input, and then pick one from A and B. In the process we just mentioned, every time decoder picks the one with the highest score, right? Do you remember that we always pick the maximum one? So, we assume the score of A is 0.6, and the score of B is 0.4. The decoder will output A for the first time. Then, we assume the score of B is 0.6, and the score of A is 0.4. The decoder will output B. Alright. Then, we assume that B is used as input. Now, there are A and B for inputs. Then, next, the score of A is 0.4, and the score of B is 0.6. Then, decoder will pick B as output. So, the outputs are A, B, and B. Looking for the token with the highest score every time like this. Or looking for the word with the highest score every time, as output is called greedy decoding. However, is greedy decoding necessarily the better method? How about not choosing the token with the highest score at first? For example, even though B is 0.4 in the first step, we still choose B nonetheless. If we choose B, perhaps the possibility of the next B will greatly increase and rise to 0.9. And for the next 3 steps, the probabilities of B are also 0.9. When we compare the red route with the green route, we can see that even though we chose a slightly worse output in the first step, the overall outcome of the green route seems to be better than the red route. We didn't choose the optimal route in the first step, right? However, the result seems to be better. So, when we compare the red route with the green route, the first step of the red route seems to be optimal. However, the overall outcome is worse than the green route, whose first step doesn't seem optimal. So, should we actually choose the green route instead? Do you know what this reminds me of? This is just like pursuing a PhD. It is a turning point in your life, and many people face difficulties when deciding. If you choose to pursue it, you might go through a tough time. But it's ultimately better in the long run. If you choose not to pursue it and look for a job instead, you might make more money in the short term. But that might come at the cost of a better future. So, should you pursue a PhD? Or not? Well, since the PhD degrees in our school aren't really popular, I'll advertise them every now and then. Okay, back to the topic. How can we find the best route? Maybe we could list out every possibility. The problem is that we actually can't search all possible paths because there are too many choices for every turning point. Take Chinese for example. There are over 4,000 Chinese characters. So, there are 4,000 possible paths at every fork of this tree. After 2 or 3 steps, the number of total possible routes grows too large. What should we do, then? There is an algorithm called beam search that uses a more effective method to find an approximate solution. As the name suggests, the approximate solution is not the most accurate answer. This technique is called beam search, and you can search it up yourself. So, is beam search actually effective? The interesting thing is that it is sometimes useful, and sometimes not so useful. Some researches have shown that beam search is completely useless. How come? For example, in this paper called The Curious Case of Neural Text Degeneration, the task they're trying to do is sentence completion. That is, the machine reads the first half of the sentence first and tries to fill out the second half of the sentence. You can give it the first half of a news article or story and watch it fill out the rest of it, using nothing but its imagination and creativity. We can see that using beam search in this paper is quite problematic, and it is stated at the start of this paper. If we choose to use beam search to complete this task, the machine will keep on repeating the same words over and over again and fall into an infinite loop. If we choose to not use beam search and add some randomness to our decisions, the result may not be perfect, but at least the sentences look normal. So, what's interesting is that, for the decoder, sometimes it's better to not find the route with the highest score. You might feel a little confused at this point. Didn't we just show in the previous slide that we want to find the route with the highest score? Now, suddenly you're telling me that it's not necessarily better to find the route with the highest score. What's going on? Well, it all comes down to the nature of the task. Let's assume a task that has a very clear answer to it. What does it mean to have a clear answer? For example, for the task of speech recognition, there is only one possible answer for each sentence, which is the text of that sentence. There is no gray area for that. In my opinion, beam search will usually be more helpful for these kinds of tasks. Then, what kinds of tasks are beam search not helpful for? When we need the machine to be a bit creative, beam search is relatively unhelpful. For example, the task of sentence completion. When the machine is given the first half of the story, there are endless possibilities for the second half. These kinds of tasks that require some creativity and have no definitive answers often require some randomness to be added in the decoder. There is another task That also requires some randomness in the decoder, which is the task of text-to-speech. Text-to-speech, or TTS in short, is a very memorable task for me. Back then, when our lab was trying to do text-to-speech using the sequence-to-sequence model, we failed a lot of times and couldn't quite figure out why. One time, someone from Google came to visit our lab, and we asked about his opinion on this matter. He said, "Don't you know you have to add noise to the decoder when doing TTS?" It sounded absurd. This is very counterintuitive and quite unorthodox. We know that in the field of machine learning, we sometimes add noise during training. For example, we might add dropout during training. We haven't covered dropout yet, so some of you might not know what it is. If you don't know what dropout is, imagine that we add some noise during the training phase. This way, the machine sees more diverse possibilities throughout the training phase. This will make the training process more robust and allows the machine to adapt to situations that it has not seen before. While this is common practice during training, adding noise during the testing phase is counterintuitive, since intuitively speaking, that should make the result worse. But this is exactly the special part of TTS. During testing, it is better to add some noise beforehand to achieve better results. Sounds magical, isn't it? If we use the normal decoding method, the sound we obtain sounds like a machine gun. You might not be able to recognize that the sound origins from a human speaking. But adding some random factors during decoding results in better sound quality. This is a very interesting fact. Randomness in decoders might improve the results. This is also consistent with an English proverb, except that nothing is perfect. True beauty lies in the cracks of imperfection. In tasks such as TTS or sentence completion, the best result the decoder can find might not correspond with the best result we found. And that's why adding some randomness can give better results. There is still another problem. Let's take our homework as an example. In our homework, the evaluation criterion is the blue score. How is the blue score measured? After the decoder generates a sentence, we take this sentence as a whole and compare it with the correct answer to calculate the blue score. But we don't do that while training. During the training phase, each word is considered separately. Also, we are minimizing the cross-entropy. The question is, can we really maximize blue score by minimizing cross-entropy? Obviously not, because these two are not the same. They might be a little related, but not much. After all, they are two different functions. So minimizing cross-entropy does not necessarily maximize blue score. That's why we choose, in the sample code provided by TA, the model with the highest blue score as the best model, but not the model with the smallest cross-entropy. So the loss function for training is cross-entropy, but the evaluation criterion is blue score. So you should use blue score for the validation set, right? Then some of you might ask, why don't we optimize the blue score during the training phase? Can we define the loss function as negative blue score and minimize the loss? Because if you can minimize negative blue score, you can maximize blue score itself. But the reality is not that simple. Of course you can take blue score as the optimization function, which you hope to maximize. But the explicit formula of blue score is very complicated. And even worse, it is not differentiable. If you treat it as the loss function, you don't even know what to do. The reason we use cross-entropy and calculate the contribution for each character separately is because this is the only thing we know how to do. On the other hand, the blue score between two sentences is not even differentiable. Then what should we do? I'll teach you a trick here. Whenever you encounter a problem that you can't solve by optimization, simply use RL, thinking of the loss function, which you can't optimize, as RL's reward, and treat your decoder as the agent. Then you can try to solve the whole problem. By reinforcement learning, then you might be able to solve the problem. Had anyone actually tried this? The answer is yes. I will list the reference here. Of course this is a difficult approach, and I don't recommend you to use this trick in your homework. Now let's talk about the topic I'd been mentioning repeatedly. The inconsistency between training and testing. While testing, the decoder sees its own output, so it might encounter something wrong during testing. But the decoder receives completely correct answers while training. This inconsistency is called exposure bias. Since the decoder had only seen correct answers while training, once it makes a mistake during testing, all the following steps are likely to be wrong. Because it has never seen a wrong answer, it will be very surprised when it sees a wrong answer, thus resulting in errors. Can we solve this problem? One possible way is to add something wrong to the input of decoder. This method is very intuitive. You don't give decoder correct answers only. It will learn better if you give it some wrong answers occasionally. This trick is called scheduled sampling. It's not the same as the schedule learning rate that TA just told you. That one is totally different from this one. Scheduled sampling is actually a very old technique. It first appeared in a paper 15 years ago. At that time, transformer didn't even exist. Scheduled sampling had already been proposed when people are still using LSTM. But this technique actually harms transformers' ability to parallelize. You can study the details by yourself. The point is, the originally proposed scheduled sampling for LSTMs and the scheduled sampling here for transformers are two different tricks. I will put all the references here. Okay, we've finished discussing the transformer and its various training techniques. We've talked about the encoder and the decoder and the relationship between them. Also, we've talked about methods and tips for training. Okay, let's stop here for a while and answer some questions if you have any. Any questions? Does any student online have questions? Good. If you don't have questions, let's take a break for 10 minutes. We will come back in 10 minutes.